Hello. In this lecture, we're going to talk about functional analysis. And our focus here is with the formulation of least squares adjustment and also to offer a geometric perspective of the least squares adjustment. We are going to cover linear spaces and commutative diagrams. The reference for functional analysis is this book by Kreisig, written in 1978, Introductory Functional Analysis with Applications. I really like this book quite a lot, and it is available on our UNB libraries. So functional analysis is a branch of mathematics that deals with functionals. And what are functions? Functionals are functions of functions. So a function is like a function. Is a relationship between objects, but the objects may be numbers, vectors, or functions themselves. And when we group these objects, we call these groupings spaces. So we're going to talk about spaces. So we need to define properties for these spaces, and we also need to define the relationship and how these relationships will be translated into transformations. So we need to define or revisit the concept of linear independence. What are linear independent functions? So what are linear independent functions? So we can say that the two functions are linear independent on any interval I. If we can establish the relationship like these, we have the functions multiplied by a particular scale k1 and k2. The summation of these products equals to 0. So this implies that k1 and k2 are equal to 0. If that condition is applied, it means that they are linearly independent. Okay, if k1 or k2 are different from 0, we can establish then relationships, linear relationships between them. So which means they are now linear dependent. There is linear dependence between them. So y1 and y2 form a basis, or we can think of a fundamental system or axis of a coordinate system, if and only if they are linearly independent. And functions or variables are said to be orthogonal if they are uncorrelated, if they are independent. So we can see these easily in 2 dimensions or in 3 dimensions, but that happens in any dimension. It's just difficult for us to see, visualize, or to imagine what 4-dimensional or 4-dimension and up space would be, a coordinate system would be. So we can define linear spaces as any space which contains elements that are known as vectors. And the property of these vectors will be the vector addition and vector multiplication by scalars. So we have the commutative property, which is given here, given 2 vectors A and B, and it doesn't matter how we add them. Associativity, we can add 3 vectors in different ways. The 0 vector property, and also the uniqueness of a vector. So for every vector A in this space V, in this linear space or vector space V, there is a unique vector minus A. The multiplication by scalars is defined by the distributivity property. It can be written in a different way here. And if we have one scalar multiplying the summation of two vectors, or the summation of two vectors be multiplied by one scale. The associativity and also when it's multiplied by 1, by scalar equals to 1, we retrieve the same vector. A complex vector space is obtained if we take complex numbers instead of real numbers as scalars. The issue of linear independence, we can just apply the concept of linear independence. We talked about functions, now we're talking about vectors. So we can establish a linear combination of these vectors with these coefficients C1, which are scalars. And the set of all these linear combinations is called the span of the vectors, so the span of the space, basically. So S is span or generated by those n vectors. If we have this particular equation, it will hold if the coefficients are equal to 0. Then these vectors a to a sub 1 to a sub n are linearly independent. If they are linear independent, they are forming the basis of that particular vector space. So if a vector space V contains a set of linearly independent set B of n vectors, whereas any set of n plus 1 or more vectors in V is linear dependent, then V is said to have dimension n, and B is called a basis of V. So again, the set B of n vectors which are independent. So the number of independent vectors define the dimension, and the set of B, the set of linear independent vectors are called the basis of V. Again, it's like a coordinate system. We also have these linear spaces. So examples of linear spaces. So we have here a vector V composed of these components, and the dimension of if V is linear, V is a linear space. So the dimension of V will be the dimension of the space. That exists a basis of any linearly independent V sub I vectors, and we can express them by this way here. So examples of linear spaces or vector spaces, we have the observation vector that we are going to call L, which is populated by observations, observation vectors. We have the parameter space, which is populated by parameter vectors. We have the model space, which is basically populated by the functions that relate observations and parameters. So the positioning in a vector space is defined with respect to a specific basis, just like point position in geometric space. So again, this is the best analogy that we can have. So geometrical representation then of a 3D, three-dimensional space. We have these three vectors, v1, v2, v3. They are all orthogonal to each other. And we have this vector v, which would be then linear dependent because they are composed of linear combination of these three linear independent vectors. How to represent a n-dimensional case? We're going to use diagrams. So this is a two-dimensional diagram that is representing now a n-dimensional case. Okay, so what we see here is the actual vector v. We are not drawing the basis of this space. Okay. So what is a mapping? Mapping is an equation that relates two vectors. So we have the transformation from v onto u. So u is the range of the function, v is the domain of the function, and the function is belongs to the transformation, a function space that transforms v onto u. Now we will be dealing with linear mappings, which basically are matrices. So, and this is the way that we usually work. We have this vector v that is transformed, or that is transformed onto this from space v, vector v from space v, which is transformed to this vector u in the space u. Okay, so the dimension of u, what we use is n, the number of number of unknowns. Dimension of v we call the m, and dimension of m is going to be n by m. So for every v we get a vector u. Example, the usual least squares relationship that we have of observations equal to the xi matrix times the parameter vector. Here we have the space of parameters, which has a dimension u, number of unknowns. Here we have a space L observations with dimension n, number of observations. And what this expression here tell us is that we are transforming x, a vector x in the parameter space into a vector a in the observation space by means of a, which is basically then a linear mapping. If we have a non-linear case, what we do is we linearize using Taylor series expansion, and this is going to yield the first design matrix, is going to yield the solution vector, and that is going to be, and we have L minus fx naught, which is nothing else but our misclosure. So what we have here then, we can, by this expression, we can see that we have a transformation from the parameter vector x to the observation vector L. So the misclosure is in the observation vector. So what we have in here now is this would be the point where we start. This vector represents the approximate value. We have delta, that's the solution vector, and finally we have here the vector, the final vector x. Okay, so the function transforms these vectors. The function transforms the spaces. The vectors are transformed by the design matrix. So we have here delta that lives in a differential neighborhood. So matrix A is transforming then into W from the parameter space to observation space. Differential neighborhood, what is W? W is again, as we can see in here, is L. This is vector L. And we have here is the difference between vector L and the function evaluated with the approximated values of x. So this is W. We may have a more complicated situation in the combined case, because the combined case will have now the parameter space, the functional space or model space, and the observation space. Okay, because here we have two transformations. We have the first design matrix that transforms delta into from the parameter space to the functional space, and we have the second design matrix B that will transform the residual into from the observation space to the model space. Let's define now metric spaces. Linear space, which has a function, a metric, a function rho, and in such a way that satisfies the axioms of a metric, is called a metric space. So what is a metric? Metric is basically a distance between two vectors. Okay, so the axioms of a metric is that it is never negative. It also, we have the commutative. The distance, basically the metric between distance A and B is the same as distance B and A. So that's the commutative axiom. And we have a triangular inequality. So the interpretation of a metric in an Euclidean space would be very simple. We have these two vectors A and B, and here in blue we have the distance between vectors A and B. We can now define a normed space. A normed space is a linear space with this function that is called the norm of the vector. What is the norm of the vector? Is essentially the length of the vector. So the axioms of a norm for two vectors A and B and a scalar in the which is a real number. A and B are in this space V, linear space V. We have the non-negativeness, which means that the length of a vector is going to be 0 or always positive. And we have linearity. We can multiply a scalar by a vector and compute its norm, or we can compute the norm of vector and multiply by the scalar. And there is also the triangular inequality. So the interpretation of a normed space in an Euclidean space, in a geometric Euclidean space, is basically the length of the vector. So here we have a vector A, which is indicating here the norm of the vector. Okay. Let's continue. Hilbert space. A Hilbert space is a space that contains a scalar function. Okay, this guy that looks smiley face, it's the scalar function. So which means that we have the scalar product, scalar function, I'm sorry, the scalar product between two vectors A and B. We're defining here vectors A, B, and C that belong to this linear space V, and also the scalar that is a real number. We have the non-negativeness. So the scalar product is going to be either 0 or greater than 0, the commutative, linearity, and there is the associativity. It must be to be complete, automatic if dimension is finite. So which means the limit of a series must also be in the space. Interpretation in the geometric Euclidean space of a scalar product is orthogonality. So the linear product between vector A and B will be the projection of vector A onto B. Quadratic norm, we have these, the quadratic norm is basically, well, it can be represented different ways. This is the square root of the product of A transpose A, or we can also consider just the square of each one of these elements. So if we have this quadratic norm, we have the Euclidean distance, or the mean quadratic, which is basically similar, we can see as a similar thing, but now it is basically the distance, or the norm, between these two vectors A and B. Okay, and can be represented likewise in matrix form or in a summation of the square of its elements. And then we have the Euclidean scalar product between two vectors. This is the again, scalar product, which is basically the product of the of each one of the elements of the vectors A and B. And these, of course, all these quadratic norms and the Euclidean distance and the Euclidean scalar product, they have a close relation with least squares. We can define a more general metric space, which is essentially the space that we use in the adjustment. When we define the quadratic form, we add a matrix P, which is a positive definite square matrix that can be called the metric tensor of the space V, of the linear space. And this is basically the weight matrix that we use. So this metric, if you add this metric, we're going to have now a norm that will be also weights, and the inner product will also be weighted. The consequence is a statistical input. What does it mean? It means that now we have a probability space. Okay, and the probability space is a space that every subspace is such a space, every subspace of which is mapped on 0 to 1. That's a probability, 0 to 1, 0 to 100%. So this is called a probability measure. In one dimensions, we have this measure closely related to weight. In several dimensions, we get the inverse, the weight matrix, inverse of the covariance matrix of the observations. Again, play the role of a metric tensor. So if we have a Hilbert space, and what is a Hilbert space? The Hilbert space is a space that is linear. It has a metric, it has a norm, and it has a scalar product. If it also has probability, it's also probability space, then we have a probability Hilbert space. So in a probability Hilbert space, we can do everything else plus statistics. So applications in adjustment, what we have here, we are going to consider these three spaces, observation space, parameter space, functional space. They're all probability Hilbert spaces with metric tensors. We have the weight matrix of the observations. We have the weight matrix of the parameters, that's the inverse of the covariance matrix of the parameters. We can also have a weight matrix for the, well, should to be strict in following the function analysis jargon. I should call these metric tensors. But anyway, that's what we how we call in adjustment. This is the inverse of the covariance matrix of the misclosures. And so we can talk about distances between vectors, distances between parameters. We can talk about the norms of these vectors. We can talk about scalar products. So the basis of least squares is the minimization of the distance between AX and L. Two vectors, vectors AX and L. Rho is the probability measured mean quadratic distance. So if we have the minimization of these two quantities here, of this distance, this is basically the residual. So we can actually draw something like that. This is AX. This is L, and this here is the residual. Okay, this is the residual. This is actually would be this, the distance. Well, we can consider that as a vector. This is spanning a kind of a hyper surface containing L. But anyway, we have now this is the solution for least squares that we call the minimum quadratic norm solution. Okay, and and that's why we call minimum quadratic norm solution, because we want this quadratic norm, okay, to be minimum. Okay, the minimization of the square of the residuals. Let's talk about commutative diagrams. We need to introduce the idea of dual spaces. Let's consider two linear spaces A and B. They are going to be dual if there is an isomorphic correspondence of all elements, which means each element corresponds to another one in one space. So element in A corresponds to an element B, only one element B, and vice versa. So each element of the vector B that is in B is a linear combination of the vector A that is in space A. Again, we have this relationship with a linear mapping. If we want to go from A to B, we have these linear mapping T, and going from B to U, we have these linear matrix, linear mapping U. Okay, and if you go from A to B and then from B to A, what is going to happen is that we're going to see that the product of U and T is identity. Okay, so in other words, the matrix U is a transpose of matrix T. So let's look at this idea of the dual spaces. Instead of L, A and B, let's call L and L star. This is the prime space. This is the dual space. So we can relate the prime space and the dual space by the weight matrix, matrix P, and we can relate the dual space to the prime space by the inverse of the weight, which is the covariance matrix. Okay, in this case here we're dealing with observation spaces. So this property now allow us to build what we call the commutative diagrams. So a rule to work with commutative diagrams is that we start from the point of arrival and work backwards. And we must not commute operators. So, which means it's commutative because it doesn't matter the direction that you go through, the solution is going to be always the same. We are going to look at the commutative diagram. Let's work on an example of the linear parametric model. So what we have in here is we have the prime spaces and we have here the dual spaces. So we have the observation space and the parameter space. So this is the prime of the observation space. This is the prime, this is the dual of the observation space, prime of the parameter space, dual of the parameter space. So we have a vector L of observations, a vector X of parameters. This diagram will tell us that L equals to AX. Okay, again, if we want to arrive at L, we start from X and move to L. So this is A here, the design matrix. What about the opposite? How can we link parameter and observation? So in this case, what we need to do is we're going to start from L and go all the way to X. So L multiplying PL, this is the weight matrix. Sorry about that. PL then we multiply, we use A transpose and CX. We know that the CX is an inverse, and we know that an inverse is A transpose PL A, and we have inverse here. So which means this equation, it boils down to be the equation of the linear parametric adjustment. So we have just we just have gained a different understanding of the least squares process. We are moving from the observation space to a parameter space, going through the dual of the observation space, the dual of the parameter space, and arrive at the prime of the parameter space. Interesting, eh? What about the conditional model? So what we have here now is 1, 2, 3. Now we have the example of the for the linear conditional model. So the diagram, again, we have the prime space and the dual space. The relationship between prime and dual, or the weight matrix or its inverse. And we have here the same. The relationship between the observation space and the model space are the design matrix, and we know that in the condition model we use the second design matrix. So how does it look like? Okay, I'll let you work on this. Now, finalize. Let's make sure that we understand about what is normal, what the meaning of normal equations. So here we have, we can say what is normal in the normal equations. Here we have the normal equations for the parametric model. And to simplify, I made the covariance matrix equals to the identity matrix. So if we perform these, the product, we're going to say that K transpose times A equals to 0, and K, if you recall, is the Lagrange correlates. The residuals are equal to the Lagrange correlates, and the misclosure is the difference between residuals. This is observation space, and A delta. And now we know every time now that we look at this expression A delta or AX, we know that we are transforming delta. This is parameter space going through the design matrix. These results in observation space. So let's look at these now from a geometric perspective. So K transpose equals to 0. This is a normality condition. The Lagrange correlate vector is orthogonal, it is normal, to the column vectors of A, of matrix A. And then the second equation tells us that the residual vector equals to the Lagrange correlate. Okay, which means that the residual vector is also orthogonal to the column vectors of A. And then we have this expression here that relates the misclosure decomposed as the sum of the residuals and the vector minus A delta. So minus A delta, we are multiplying delta by A. This vector, it lies in a space generated by the columns vector of A. Okay, so A delta is, well, it rests on these on the space that is generated or spanned by matrix A. Okay, and here we have the misclosure vector, and we know that the residual vector is orthogonal to the column vectors of A. Okay, so the residuals are normal. Okay, so which means that we can now say that we know what is normal in the normal equations. So in the parametric model, the misclosure vector W lies in the observation space, okay, because the misclosure is a difference between the functional model evaluated with a point of expansion and the vector L. We can call these L sub 0 and L. In the linear model, the parametric case, this is it. The design matrix A plays the role of the linear operator mapping vector delta, which lies in the parameter space, onto the observation space. So this is what it's doing here. So we have L equals to A delta. Okay. Okay, so that all components of the linear model R, A delta, and W now live in the same observation space. So delta was moved onto the observation space by being multiplied by A. Okay, so here is A delta hat, or A delta is in the observation space, W is observation space, R is observation space. So this is now a similar diagram that we drew in the previous slide. It shows the column vectors, the columns. Yeah, that's right. The column vectors of matrix A. And we can see here A delta, which is on this plane, or this the way it looks here is a plane, but if you have much more, if the design matrix has much more columns, it becomes a funny surface. We have here the normal to this space spanned by these the columns of matrix A. This is the residual, which is normal, and here we have the observations. Okay. So, in a summary, we reviewed the concept of linear independence. We presented the properties of linear or vector space, metric space, normed space, Hilbert space, and probability space. We reviewed the concept of mappings and linear mappings. We introduced the concept of mappings and linear mappings. We introduced the concept of dual spaces and commutative diagrams. We analyzed the concept of normality from a functional analysis perspective and what is normal in the normal equations. And we stop here.